Welcome to qnawire.
We're going to talk about Joules' experiment, in which the main goal was to measure a certain quantity coming from the internal energy for a system. So remember that the internal energy of the system is going to be equal to du. Du is equal to the partial of u with respect to b at constant temperature times dv, plus the partial of u with respect to t at constant volume times dt. So the second term over here is known. This is going to be the value for Cv. So our expression for du is going to be equal to the partial of u with respect to ub, with respect to the volume, t dv, plus Cv dt. And essentially what Joules wanted to measure is this factor over here. He thought that this was going to be something as an internal pressure of the system at constant temperature. The reason why he labeled this as an internal pressure is because of the units of energy divided by volume. So remember that energy divided by volume is going to give you units of pressure. So his experimental design was the following. It is going to appear as a drawing because it would take too long. So, in which we had two containers A and B that are connected by a valve that is initially closed. In container A, we're going to have molecules of a certain gas, and in part B, it is going to be completely empty. It is going to be at a vacuum. The idea is that when you open the valve, the gas is going to expand. That means the delta B is going to be larger than zero. The external pressure against it's going to expand is going to be equal to zero. So there is not going to be any work done. And with that, he's going to be able to measure the quantity that we just described. In the way that he was going to be able to measure it was considering that du is equal to dq plus dw. In the case that external pressure is equal to zero, the work is going to be zero, so dq is going to be equal to du, and as we mentioned, it was going to be equal to this factor of pressure that he assigned to the partial of the internal energy with respect to volume at a certain temperature plus Cv dt. So we can measure directly what is going to be the temperature. The change of volume is going to be given by the volume of the second sphere. And what he observed was that dt was equal to zero, since dq was equal to zero. So what he thought was that the partial of u with respect to b at a constant temperature is going to be equal to zero. So this was the conclusion from you. Of course, this is not going to be true. Later or probably in your course, you're going to see that the partial of u with respect to b at a constant temperature is equal to t times the partial of p with respect to t with respect to volume minus p. This is the general relationship but for that factor. But the shortcoming of his experiment is that he's not going to be able to measure small changes of temperature. Since he was not able to measure these small changes of temperature, then he assumed that the value for dq was exactly going to be equal to zero. But curiously enough, with this you can actually find the limiting behavior for an ideal gas, for ideal gases. Why is that? Because if we take the ideal gas equation, P is equal to nRT divided by B, what happens is that if we take the partial of P with respect to temperature at constant volume, what we are going to get is that this is going to be equal to nR divided by B. Substituting this into our equation over here, into the true relationship, what happens is that partial of U with respect to B at constant temperature for ideal gas is going to be equal to T times nR divided by B. And guess what? This is going to be equal to P, right? So this becomes P minus P, and this is going to be equal to zero. So the other limitation that we're going to have is that in the Joule experiment, if we're employing gases under conditions in which we can assume that they are ideal gases, then the value needs to be equal to zero. The amount of heat coming from the system will be directly zero. So that is why we know that the internal energy for an ideal gas is only a function of temperature and not a function of the volume, which is going to be the main conclusion nowadays from the Joules experiment. So with that, it would be all. Just to recap, the experimental design, the main drawback is that he wasn't able to measure small changes in temperature. The other possible drawback is that depending on the conditions, the gases that he employed or the ones that you employed while replicating the experiment can be assumed to be ideal gases or are close to ideal behavior. So what you're going to see is that this partial derivative view with respect to being at constant temperature, which he referred to as an internal pressure of the system, is going to be equal to zero. So this is like the proof that that is going to be true for an ideal gas, and it would be all. Thank you very much, and have a good one.